Our guest speaker, or the first speaker today, is Anthony Williams. I'm very pleased to have you on the online conference. Thank you for coming. Thank you for preparing your talk, Anthony, about multithreading and C++20. It's an interesting topic. Please take it away.
Okay, so thank you. I'm going to be talking about multi-threading in C++20. And so first off, then I'm going to be making some simplifying assumptions. The first one is that we're starting a new project, so we don't have to worry about existing code and compatibility with what we've already got. And secondly, that we've got a C++20 compiler and library. So lots of the things that I'm going to talk about will still apply if you've got C++17 code or C++14 code, but specifically we're going to be focusing on the C++20 stuff, so you probably need the C++20 compiler. So the first thing that I'm then going to talk about is how you choose your concurrency model, because that's the basis for what you're building in your multi-threaded application. You're going to have a think about why you're looking for concurrency and multi-threading, why that's the solution that you want to use, and what benefits you're hoping to achieve. And then that can affect the way that you structure your code. Then I'm going to look at how to start and manage threads using the C++20 library. And then finally, we'll look at the library facilities that we have for synchronizing data. So when you're choosing your concurrency model, then fundamentally, then we can divide our applications into sort of two different types, based around the fundamental reasons why we're wanting concurrency. The first reason that you might want concurrency is you want scalability. You intend your application to run not just on the computer that you have today, but that you want to run on the computer that you're potentially going to buy next year. Or alternatively, that today then your software is going to be running on customers' computers, and that they vary in the power that they have. If you're trying to run on a desktop Windows machine, for example, then some people might still have single core or dual core computers, and other people might have Threadrippers with 64 cores. And if you want your application to work seamlessly and take advantage of the more cores, then you need it to be scalable. Similarly, if you're writing library code, then you might find that you want to scale your library. If it's some form of number crunching library, then you might want it to scale with the system that it's running on, and potentially it's running on again desktop computers, or possibly it's running on server computers which have more cores, or possibly it's running on an HPC rack which might have thousands of cores, and you need to scale across the whole facility. And you're looking for that scalability. You're wanting to write software that runs faster in whatever metric that's important to you as the processing power increases. And on the other hand, then you might be using multi-threading as a means of separating of concerns. You have some things which your application does, some of which can run concurrently. And so rather than doing the complicated code necessary to multiplex those on the same thread, then you leave that to the operating system. You say, well, there's this part of the application which runs concurrently with that other part, and you, as the operating system, can make use of the available execution facilities to actually run those two parts concurrently, either by interleaving and time slicing, as has been done on computers for decades, or then potentially taking advantage of the multiple CPUs and multiple cores that your system has as they become available. So if you're, for example, you're a developer and you're running your editor and you want it to highlight syntax errors in the background, you don't want that to get in the way of you actually typing in new code, or but you do appreciate the red squigglies. So you might have a background thread in your editor that does that compilation, or potentially even invoking a background process to do that. And so that's a pure separation of concerns facility, because we want to maintain that responsiveness in terms of having both parts still running whilst actually taking advantage of the multi-threading facilities. And which of those you choose fundamentally affects the structure of your code. So they inform our choice of concurrency model. Okay, so if we're thinking about scalability, then what we're really wanting to think about is the speed up that we get from parallelizing our code. We want that when you run it on a system which has more cores, then we want it to run faster. And so we have what's known as Amdahl's law, which applies in this case. Now, the speed up S is 1 divided by 1 minus the fraction of your program that can be parallelized plus the fraction that can be parallelized divided by the number of processes. It looks relatively straightforward, but if you stick in the extremes here and you say, okay, well, at 100%, so our fraction P is 100%, so that's 1, then 1 minus P is 0, and 1 over N is 1 over N, but 1 over 1 over N then becomes N. So if you have 100% of your program is parallelized, then the speed up is just how many cores have you got, and your program multiplies and scales nicely. But on the other hand, there's very few programs that are 100% parallelizable, because at the very least you have a bit of startup and a bit of at the beginning, and then some sort of form of serial termination at the end. So we don't have that in practice. So what do we get? So let's stick some more numbers in. So if 90% of our code, of our program's execution can be parallelized, you might think, well, that's a reasonably high number. But that actually isn't necessarily as good as you might think. Now, even on 1,000 cores, then that still only comes out as a 9.91 multiplier on your speed up. So we're not even 10 times faster on 1,000 cores if we have a 90% of our program can be parallelized. So obviously, and this is when we're looking at the whole program, but what you really want to do is you want to say, well, I don't mind about the startup. I don't mind about the shutdown. What I really want is I've got this core data processing part that I want to worry about. So when the user clicks go on the GUI, and then I want it to take advantage of all those 1,000 cores and do the processing really quick until we get to the end. And so fine, you can say, yeah, we can trim down the fraction of the program that we care about to just really the bit that's been trying to be processing. But still, 90% being parallelized might have seemed like a reasonable thing. But it still only gets us 9.9%, 9.9 times speed up. And obviously, if we put in 100,000 cores, then and still only getting 9.99, and we haven't got a 10 times speed up from 100,000 cores. So if you're looking for speed up on scalability, you really need to push that fraction higher of how much of the code you're caring about can be parallelized. Any single part of that that's going to take away from the pure parallelization is going to hurt your multiplier in a big way. If we can get it to 99%, then on 100,000 cores, we still only got to 99.9 times speed up, not even 100 times speed up on 100,000 cores. So you really do have to push this all the way to the limit to get us. For the part of your program that you're wanting that scalability for, you really have to make sure that there is nothing there that's going to get in the way of the parallelization. Okay, so having looked at the potential speed up we can get, we then have to look at how can we do that. And one way of doing that is the standard library algorithms, because they have parallel versions. You can pass as the first parameter, before the additional standard sequential code parameters, we have an additional execution policy. So, for example, if you're trying to sort a big vector, then you might say standard sort with standard execution par for parallelize as our first parameter, and then we pass in the normal range and the comparator just the same as ever. And this tells the standard library you want to use parallelization for this. You want to do that sort in parallel using the available cores from your CPU. And the standard library will do its best to accommodate that. And therefore, it will take advantage of the things. Now, obviously, it's not required to. It is a legal implementation technique to just say, well, I'm going to ignore that execution policy, always run it single-threaded. And sometimes it's not worth it because there is overhead in dividing up the data and managing that parallel execution. And if that means that then the fraction that's actually being parallelized is now only 10% of the runtime of the sort, then it's just not worth the overhead, and you probably get better performance just by doing the single-threaded execution. And implementations sometimes have heuristics in them that make that choice. So for small sizes, where small might be less than 1 million elements or something, then it does it serially, and then larger, it does it parallel. And obviously quite what the details of that heuristic are will vary from implementation to implementation. Now, we mentioned about we're looking at scalability. Perhaps you want to avoid anything that's going to avoid prevent parallelization. And if you have consecutive calls to parallel algorithms, then because with the way they are currently specified, then they have a serialization point in between. So in this case, we have a call to transform, which is parallelized, and that will then do its parallel execution, gather all the results, and then finish and return back to the single thread that started it. Then we have a call to standard reduce, which again is parallelized, and again it farms out the data to the parallel to the different threads that are going to run the parallel execution, and then it serializes them back again at the end. And that serialization in the middle reduces the parallelization capability. So if you can, you want to combine your consecutive calls. In this case, then we have transform reduce as a combined algorithm that therefore doesn't have that serialization step and therefore increases the potential for parallelization in our code. This is transform reduces C++'s answer to map reduce, as people might have heard of from larger scale systems. And in practice, it's really quite a general facility, and lots of things that you would like to parallelize can be altered and adjusted so that you can express that as a call to transform reduce, often with a series of range adapters. So using the C++20 ranges library in order to map and adjust the data that's being accessed so that you can then make it into a single transform reduce call. And that will therefore help with the parallelization. But it can be complex to make that work. Okay, so the other thing that you can do is you can split your work into independent tasks and use a thread pool. And this is you can do this for parallelization if you've got rather than using the parallel algorithms yourself, the ones that are provided by the library, then you can say, well, I'm going to manually divide up my tasks into a whole load of small pieces, and I'm going to give them to the thread pool, and it's going to execute them all. Alternatively, then you can use thread pools for concurrency-based things, where you have, I have this, this part of the application that needs to run, and this other part that I want to run concurrently, so I'm going to run them both on the thread pool. But if those tasks are long running, then that's not necessarily the right choice, and you might be better served with dedicated threads. But either way, you're dividing your work into many independent tasks, and then you put them on the thread pool, and the thread pool then runs them on the available hardware, and it will run more of them concurrently if the hardware can do so, and fewer of them concurrently if it can't. And obviously, quite the details will vary on your thread pool implementation. Sadly, we don't yet have a standard one, so we're looking at non-standard extensions. things like Intel threading building blocks or various other third-party thread pool libraries that you might get hold of. But we're hoping that we will get standard thread pools soon. Aiming for the C++ 26 standard, but so fingers crossed that we'll actually get there. So I touched on how you might want to use those thread pools for separation of concerns, but really, we're looking, when we're thinking about this, we're often thinking of large sequential tasks. And so we're looking at literal raw performance is not necessarily a priority. So we want things that can run concurrently. We're thinking of things that can run in the background, like background compile or spell checks, or possibly even printing, where we want the task to continue as a long-running thing, but we don't want it to interrupt I'm going to call it the primary task of our application, or we want multiple things to run concurrently, but direct raw performance isn't the gain, although obviously if they can run truly concurrently, then that is nice. But we don't want to actually have to write the multiplexing ourselves. We want the operating system and runtime library to do that for us. So you might then run long-running tasks on their own thread rather than putting them on a thread pool, so that then the operating system is aware that this is a dedicated thread for this task. You might have a thread that's running the GUI, or a thread that's doing printing in the background, for example. Now note here, in this example, then standard Jthread is a new class from C++ 20 for managing threads. And you pass it something that is callable, in this case lambdas, to the constructor, and it then starts the thread automatically. Which neatly brings us on to starting and managing threads. Though, actually first, I'm just going to take a detour. We're going to talk about cooperative cancellation. Now, see, we all use GUIs all the time that have cancel buttons. Now, you might have it downloading a file, you might have it rendering a video, you might have it printing something, whatever. There often is a cancel button. And we want our cancel button to actually stop that operation fairly promptly and then tidy things up nicely. Obviously, you don't need a GUI to cancel operations. You might be doing things on the command line. There might be internally in your application that you start some task in the background, and then you decide it's not needed anymore, and maybe the source data that it was operating on has changed, and so it's now going to give an incorrect result. So we want to cancel that operation, and we'll restart it with the new source data. But whatever we're doing, forcibly stopping a thread is undesirable. If you actually use low-level operating system calls to brute force cancel a thread, then who knows what state your application is in, because the destructors in that thread have not had a chance to run, so it might still be holding locks, it might still have open files, it might have partially written data that it was intending to synchronize to share with other parts of the application, but it's now just left in a half-finished state. So you don't want to do that. You don't want to forcibly stop a thread. So you want to have some means where you can ask it nicely to cancel and tidy up. And in C++ 20, this is done with the standard stop source type and the standard stops token type. It gives us cooperative cancellation, and it is purely cooperative. If you send a cancellation signal and the target task doesn't check, then nothing happens. It's not going to interrupt the task in a forcible fashion. It just sends it a signal that it can check. It's a flag. I'm going to ask you to stop, and if the code doesn't look, nothing happens. So how would you use it? Well, first of all, we create a stop source. It's just default constructible. That's dead easy. Then we ask the stop source to give us a stop token. This stop token is copyable. We can pass it around to as many places as we like. So we can pass it to a new thread or a task that we've submitted to a thread pool. And then when you want the operation to stop, you call request stop on your stop source, and that then sets the flag. At some point, then the task that we're hoping to interrupt will call the function on its token, stop requested, which checks to see if the flag has been set and returns true or false. If the call to stop requested returns true, then it's up to you to stop the task, do something with that signal. And again, to reiterate, if you do not check the stop token requested, nothing happens. If you check it and discard the result, then nothing happens special. No, it's up to you. This is a cooperative mechanism. So what does it look like in code? Well, here we have two things. We have our stoppable function, where we take a stop token as the parameter, and then typically you'll have some while loop or maybe a for loop or something with an exit condition, but it's going to check the flag every iteration, and while the flag has not been raised, we're going to do stuff. And then when the flag is raised, then stop requested will return true, and while loop exits. On the other side, on a different thread, we'll have our stopper function running, which takes the stop source. It's a movable thing, so you can transfer ownership in, pass it by value. And then while we're not done, where we're actually checking to see whether there's something that's happening that means that we now want to stop, then we're going to do something. And then when we've finished, when our done flag is true, then we're going to ask the source to request that the other thread stops. And that will set the flag and break us out of the while loop in our stoppable function. You can also use stop callback. Now, this is actually one of the most powerful parts of this mechanism. It gives you a means of putting cancellation around any mechanism that can be cancelled can then be used with stop tokens. So if you have, say, an async IO library that you're using that gives you a function for cancelling pending IO, then you can then integrate that with stop tokens by using a stop callback. So we take our stop token, we open our file to give us a handle. We then register the stop callback that says, if we're stopped at this point, then I want to call cancel IO, which will stop the pending IO on this operation on this handle. And then, so having registered our stop callback, because we've created the object CB, then we can then call our blocking call, read data on this handle. And now this would normally be a blocking call, but if a stop token, if the stop token has its flag raised, then the stop callback is invoked on the other thread, on the thread that actually set the flag. And that will then call cancel IO, which will then interrupt our read data call, and we can then return. And in this case, obviously, it's returning the data object, which maybe it's some partially read data, or the data object contains a flag that says actually I was interrupted or whatever. But the point is that now, previously we would have had to know that the other thread was doing IO that we used to, and would need to know which handle it was so we could call cancel IO on the handle. Now with stop callback, we don't need to know that. We don't need to know what this other thread's doing. We just need to know it's doing something that we can stop. And so we set our flag with the stop source, called request stop, just like we did before. And then the callback identifies the exact function that we need to call in order to do that interrupting. So this is, like I say, it's a really powerful mechanism. You can use it for anything that has some means of interruption that you can use because you can register it with the callback. Okay, so having just looked at cooperative cancellation, now we can go back to starting and managing threads. And so if you're managing threads manually, you want to use standard Jthread. 99% is probably too low, a fraction. 99.99. It's what you want to use if you have it as an option and you're trying to manage the threads manually. Obviously, ideally, step back, we're going to use thread pools, because if you can let the library manage the threads entirely, then that's a good choice. But if we're managing threads directly ourselves, Jthread is the answer. Well, sometimes you don't want. Sometimes you actually want to run the thread, and it's going to give you a value as a result. It's going to run a long-running calculation and give you a value. In which case, standard async might be what you want because it gives you a future that gives you a value. But in particular, standard thread from C++11 should only be used if you have no choice. No? We're saying we've got a C++20 compiler and library and no legacy code, so we have a choice. We don't need standard thread. But if in practice you've got some other code that uses standard thread, then maybe you do. Maybe you're stuck with it. But you should be looking to migrate to Jthread if you can. So how do we use Jthread? Well, I said already, creating the Jthread object starts the thread. We pass it a callable thing. Like with standard thread from C++11, you can pass some arguments as well. So you can pass the name of a function and some arguments. You could pass a lambda that took arguments and some arguments. Anything that's callable and then arguments that are then passed. And the reason why we took the detour into cooperative cancellation first is because Jthread incorporates cooperative cancellation. When it calls your function, the first parameter is going to be a stop token. And so that stop token relates to a stop source held internally in the Jthread object. And so it gives us that cooperative cancellation option. Obviously, if your function doesn't take a stop token, then it's backwards compatible with standard thread. So you can just use it as a drop-in replacement, and it will just call myfunc with the arguments you supply. But first, it checks to see whether your function will take a stop token because it's trying to integrate with that cancellation facility. So the basic API, we have a default constructor that creates an object but no thread. We have a constructor that takes a callable and some arguments. It gives us a stop source, like I mentioned, and passes the token from there into our callable. The destructor, again, integrates with this cooperative cancellation facility. We call, when the destructor occurs, if the thread is still running, then it calls request stop on the stop source and then waits for the thread to finish. So this is quite different from standard thread. Standard thread, if your thread was still running, it would terminate your program in the destructor. And you have to manually join. In Jthread, it automatically joins it. But first it says, I'm the destructor, so please stop. Somebody has asked you to actually come to an end now. And then it waits for the thread to finish. We have a function getID to obtain the thread ID of the thread that is owned, and again it returns a default constructed ID just like standard thread does if there's no thread there. And we can manually join, explicitly wait for the thread to finish, which doesn't automatically call request stop. It just waits for the thread. So if you know that you definitely want to wait for it to finish, you can just call join. Whereas the destructor will try and cancel it first. And it's a handle. It's movable. You can transfer it around as an object, like a unique pointer. Does mean you can store it in containers, which is really nice, particularly with Jthread with its automatic joining in the destructor. Means you can have a vector of Jthreads, and when the vector is destroyed, it will cancel and wait for all the threads. And whereas a vector of standard thread, if any of them were still running, it would terminate your application when you cleared them out. And there's no need to use new. Too many people who are coming from other libraries that in other languages then have a tendency to write a new standard thread or new standard Jthread. Don't do that. Just say standard thread or standard Jthread, please. And then you have it as a value that you can then move around when necessary. When you pass an object to the constructor of your Jthread, it copies the data into the internal storage so that there aren't any dangling references there automatically by default. Obviously, if you really want to pass a reference, you can use a standard ref to wrap it into a reference wrapper object, which then it copies the reference wrapper object, and that still refers to the same source. Or you can use a lambda with reference captures. But by default, because they are, say, copied, they're moved. If you pass a temporary or an R value, then it moves into the internal storage. If you just pass a reference to something, it copies. But it means that then the execution itself on the new thread is in storage that it knows about and it is in control of, and means that therefore you don't have, there's less scope for automatic dangling references. So just another, to reiterate, that the destructor requests stop and then waits for the thread to finish. So if we have our function foo here on the bottom, then we start a thread that's going to run our thread function. We're then going to do stuff, and then at the end we're going to say, well, we're done now, so we'll just drop off the end. The destructor then requests stop and joins. And in the thread function, we take that stop token as that first parameter. We then get the string and the integer that were passed in as parameters, and then we can have our while loop that's doing stuff while we haven't had stop being requested. So now that's the first way that cancellation integrates with Jthread, because it integrates with the stop token support directly. We implicitly create this stop source, which is then passed as the first parameter to the thread function. And then we have the destructor that calls request stop before then calling join. But again, it's cooperative. You still need to check the stop token, because if you have your thread function that either doesn't take a stop token or it takes one but doesn't check it, then nothing happens. That cancellation is cooperative, and if you don't cooperate, you don't get it cancelled. But we also have an API. So you can then call get stop source, which gives you the stop source that then you can actively request stop on somewhere else, because you can pass it around. You can call get stop token to get a stop token that you can say, well, when my thread is interrupted, I also want to interrupt this other task. And then, of course, you can manually request stop. So rather than having to get the stop source and then call request stop on that, you can just call request stop on the thread object. And that then sets the flag in the stop token so that the callable that's running on the other thread is interrupted. Okay, so we've started some threads, and if you're in the majority of programs, those threads are not going to work on isolated data. They're actually going to try and communicate with each other. If we're going to communicate data between threads, we need some form of synchronization, and the C++20 library provides us a whole bunch. So first thing to watch out for, though, is the dreaded data race. A data race is where you've got unsynchronized access to a memory location from more than one thread at a time, and at least one of those threads is writing. So it doesn't matter if all the if all the other threads are reading and one of them is writing, that's a data race. Whereas multiple threads reading from the same location, if nobody's writing, that's okay. And obviously 2 threads both writing, still a problem. And it's not about the actual timing. So it's not, is there a window in time when the threads are definitely both trying to access the same variable? It's, have we got proper synchronization in place? If there's not synchronization in place that forces them to be separate so that one happens before the other, then we have a data race. And the problem with data races is that data races are undefined behavior. And so therefore, your program could do anything at all. Now, the C++ standard places no requirements on what a program with undefined behavior does. It might launch some missiles, set fire to a computer, reformat your hard drive, post spam messages and your name, or whatever. So we need to put synchronization in our programs to ensure that where there is data shared between threads, we do not have data races. Like I said, we've got a whole bunch. We have latches and barriers and futures and mutexes and semaphores, and then, of course, atomics. So let's have a look at these in turn. Latches. Okay, so the C++20 latch is a single-use counter. It allows threads to wait until that count reaches 0. We construct it with a non-zero count, and then one or more threads decrease the count. It can never go up again. It always decreases. Then when it gets to 0, the latch is signaled, and threads can wait for that signal to arrive. So you can say, I want to wait until the latch reaches 0, and then other threads can signal it. But when that count does reach 0, it is permanently signaled, like a physical electronics latch. And so then if another thread tries to wait, then again it is immediately woken. So here's the API. We construct it with a count. We have count down. We have wait. We have the idiosyncratically named arrive and wait, which does a countdown and then a wait. It's called arrive and wait for consistency with barrier, which we'll look at in a minute. Which seems a bit odd with the latch API, but no, there we are. These things happen. And so how do we use it in some code? Well, typically you might use it if you've got a bunch of tasks to wait for. So we create our latch with a thread count for when everything's finished. So we've got the vector of data and a vector of threads. We're going to push back some threads to that's going to process this, do some data generation. And each of those threads, Jthread, of course, is firstly, it's going to capture by reference the data vector so that we can store our data. And we're going to capture by value the index to our loop. And we're going to call make data to generate the block of data for this thread and store that in the appropriate slot. And then we count down the latch. At this point, we're done with the shared data. The latch is signaled, and this thread can now do more stuff of whatever description. As long as it doesn't touch the shared data, it's all good. So we have that for all of them, for all of thread count threads. And so when all the threads have then reached the latch, then the latch becomes signaled. And so on the main thread, we can call done.wait, which waits for the latch to become signaled. So all the threads start, they do their make data part, they all count down the latch. They're all now still running and doing their more stuff potentially, but the latch is now signaled. And so the main thread here running foo can then process the data from that data vector, knowing that every thread has filled in its part. And even though the threads are still running, the data is correctly synchronized. Another particularly good use for latches is synchronizing tests. Because if you're trying to write multi-threaded test code, then what you want ideally is you want the threads to all be running and so that they are actually genuinely running and really competing for resources and accessing the shared data structures at the point that you're trying to test. And it is a common problem when you're writing multi-threaded test code. Actually starting the test threads takes time. And so if you don't do anything special about it, you can start a thread. Start thread 1 that's going to do some part of the test and give it some code to do. And it will start the thread immediately and run its code. Then, in the meantime, your main thread is starting thread number 2 that's going to participate in the test. But at this point, thread number 1 is finished before thread 2 even starts. Because starting thread 2 is so expensive in operation. So if instead you set up the test data and create a latch and then create the threads, and the first thing each thread does is arrive at the latch, then now you've made sure that you've moved the expensive starting of the thread before the arrival on the latch. And so these threads are actually running, or at least ready to run as best you can make it when they arrive at latch. Because they all count down and then they all wait, then when all the threads are ready, then the latch is now signaled and they all wake up. And so they're all released to run the code as close to concurrently as possible. So this is a really good way of setting up your test code. Obviously, for them to really run concurrently, you need to have enough cores in your hardware that they can and things like that. But And you're still open to the vagaries of the schedule as to whether they actually do compete and run things, but it gives you the best chance you have of setting it up. And so if you set up a test like this, and then you run the test many times, then it gives you a reasonable chance that they have actually run concurrently for the bits of code you set up in the test threads. Okay, so next up we have barriers. Standard barrier is the barrier that we have here, and notice it's a template. Though if you don't care about the template parameter, then you can just use the C++17 style argument deduction to omit those angle brackets if you like. And the whole point is that it's done in phases. So we construct a barrier with a count and a completion function. And then threads arrive at the barrier, and some of them will wait for the barrier to be signaled, and others will say, I'm not waiting, I'm count me out for this time. Then when the count reaches 0, the barrier is signaled, the completion function is now run, and then the count is reset, and we loop back around to the next phase, starting at point number 2 again. So threads arrive, they wait, the count they're all arrived, the barrier signals, completion functions run, we loop. So this is really good for where you have it's loop synchronization, and so it allows you to provide a serialization step, which it might, for those of you used to things like MPI, then this is a gather step. So you've got all the data that's been calculated, and then you want to gather the results and do something with it. So you might then, if you're encoding a video, for example, you might have the different threads are doing different parts of the frames, or one's doing the video and one's doing the audio, or something like that. And then the completion function then gathers all the data from all of them together and then ships it out into the file, and then resets the data for the next frame, and something like that. So you have this continual loop processing where you have a bunch of threads that are working on the same set of data. Then they're all done, you run the completion function, and then they all work on the next set of data, and so on. What does the API look like? Well, our template parameter is the task type, which is the type of the completion function. So you might use standard function for that, or you might use a function pointer for the task type, and then the task is actually the function or the lambda that's actually going to be run as the completion function. But crucially, you need a count. And when threads arrive, then we get an arrival token, and that decreases the count. If the count reaches 0, that can trigger the completion phase. Then when you want to wait, then you pass your arrival token into wait, and that waits for the completion to be finished. There is this arrive and wait function, the same as we had on the latch, which it combines both. It does the arrive, it immediately passes that token into wait. See, there might now not be a token because it doesn't need to do the split, but it has the same semantics. And then there's this arrive and drop, which says I'm going to decrease the count, which might potentially trigger the completion phase, and then not wait. This thread is now not waiting. It will no longer participate in this barrier, and the count is permanently 1 less. So if initially the count is 5 and some thread calls arrive and drop, the next time it resets, the count will reset to 4. It's a permanent decrease. So that's relatively straightforward. And like I said, barriers are great for loop synchronization, because we have this completion function allows you to do something between the loops. Now, this is a serial part. So if we were looking for parallelization, then this completion function saps away our parallelization because it's a serial part. Serializing in every iteration of our loop, that's just a disaster from the point of view of parallelization. But on the other hand, if you're just trying to take advantage of the processing that there is, or you've got you're doing things for not for the raw performance sake, but just to take advantage of the parallelization that there is, then maybe it still is. Having a completion function isn't such a disaster. It's actually something that allows you to separate your concerns. Here is the bit that can be parallelized. Here is the bit that's serial. Here is the bit that's parallelized. Here is the bit that's serial, and so forth. So what's it look like in code? Well, like I said, you might use a standard function as the parameter. In this case, then one that takes a function taking no parameters and returning nothing, which is good. I mean, it needs to have essentially that signature, whatever type of task you pass in there. The return type is ignored and just discarded if there is one for the completion function. So we have a completion function, finish task, and we have a number of threads, and then our worker thread will have a number of these, and they've got obviously I as the index. So we loop, and while we haven't been interrupted, then we're going to do stuff and arrive and wait at the barrier, and then all the threads will, each iteration, they will do the appropriate stuff, given I, the index, and then wait for all the other threads to do their bit, and then they will all move on to the next phase, check for cancellation, and then do stuff. What if we don't have a synchronization that can be done by a simple either one-time count or a loop? Maybe we want actually to pass some data in a one-off fashion. So futures is how we do this. It's a one-shot data transfer mechanism. I mentioned standard async as a way of creating a thread at the beginning. So this is what you can do here. With standard async, you can launch a task, it returns a value. Alternatively, you can set that explicitly with a promise, or a packaged task, which is then itself a callable thing that, rather than returning a value, it stores the result in the standard future that you can get from it separately. So in theory, you could build a thread pool using packaged task. You wrap your custom user supplied tasks into a packaged task, which then you can just have a queue of those to execute on the thread pool, and then that would return the results in the futures and that you handed out to when people give you tasks or something like that. So the basic API around the future side is the default. The constructor is always gives you an empty object. You need to get a populated one from one of the three mechanisms mentioned on the previous slide. But then you can check whether it's valid, whether it has a value. Which is true if there's potentially some shared state there. False if there isn't, if it was default constructed or has already given you the data. You can then wait for it, either just unconditionally, I'm going to wait, or you can wait for a certain duration or until a specific point in time. And then you can get the data. And get implicitly assumes that you're going to do a blocking wait if you haven't already waited. But once you've called get, then it's one shot, so the data is now gone. It returns the data, it moves it out from the internal storage and then destroys the internal storage. So, like I said, we have the blocking wait and then the non-blocking wait. So you can, if you're just going to wait and then call get, you can omit the call to wait. But if you wanted to wait and then do some other stuff and then call get, then you can. And either way, it blocks until the data is ready. On the other hand, you can take a future and do a polling check. So you can call wait for, in this case, 0 seconds, which is therefore going to return immediately. And that returns either returns future status ready if the data was there, or future status timeout if it wasn't, and deferred if you've used a particular form of async and the data is not ready yet. And then if the data is ready, then you can process it. In this case, again, you call get, but we know that the data was ready, so get won't block in this case. So how do we get a future with any content? Well, one way is from promise. And this time, if you default construct a promise, it has state. It is ready to take a value, and it's ready to give you a future. We can check whether it has state by calling valid. And we can obviously set the value. You can either explicitly set it as a value, or you can set an exception by passing in an exception pointer. And the exception is then stored in the future. And so if you call get on something that's got a stored exception, it will actually throw rather than just returning the value if there had been a value there. And then, of course, you can get the future in order to, which you can then pass to wherever you're wanting to wait for the data to come on another thread. So how might it look if we've got promise and future and we're trying to pass data from one thread to another? So we construct our promise, we get the future value from the promise, we then move that future, they're movable, not copyable, so we have to move it into the lambda that's going to our thread, and then that lambda can then call f.get and then process the result. Meanwhile, on thread 2, then we could take a reference to the promise here, or we could move the promise in. Either way works. Again, it's movable, not copyable. And then you can set the value on the promise with whatever function you have of getting the data. And so therefore, when thread 2 has executed that set value, then thread 1 will wake up from its call, its blocking get call, and then actually process the data, do stuff. Like I said, if you set an exception, then it is thrown. So in this case, we're explicitly making an exception pointer that wraps in my exception class. And then when we call get here on thread 1, it will not execute do stuff because f.get will throw, and it will throw the my exception value that was constructed on thread 2. Okay, I mentioned already async can be used to construct threads, and it's very it takes callables and arguments just like Jthread does. Doesn't do stop tokens unless you manage that yourself. But what an important part is you have to specify the launch async parameter as the first parameter if you want it to start a new thread. If you don't, then the runtime library decides, is it going to start a new thread, or am I just going to store the function for later execution? And you'll have to execute it by calling get. So don't do that. Always say you want a new thread. So you specify launch async. And then the other feature here is that in this case, the future owns the thread. So it has the same sort of destructor blocking semantics as Jthread, but again, there's no cancellation support. So if you want the cancellation support, use Jthread. If you want the value from the future, use async. Future is one shot. So after you've called get, it's no longer valid, and calling it again will throw. If you want to do it twice, then use a shared future, and you get that by calling share on a normal future. So we have our promise, we call get future, which gets us a standard future of my data. We then call .share, which gives us a shared future of my data. Then we also now, shared futures are copyable. Not only can you call get twice, but you can call it get twice on separate threads. And so we can copy them around, and both threads can call f.get and call do stuff, and it's all fine. Mutexes, low-level things, but reasonably commonly known of. But fundamentally, it's mutual exclusion, a means of preventing concurrent execution. You want to avoid it if you can. Use them as sparingly as possible. There are 6 mutex types in C++. That's 5 too many. You might say it's 6 too many because you really should be avoiding them, but really, what you want to use is standard mutex. There's variations, recursive, shared, timed, whatever. You don't need those. 999 times out of 1,000, maybe more often, don't need those. Standard mutex is the one. Always use it. If you are really profiling your code, then sometimes you might find that there are benefits to using some of the others. I think then the Visual Studio API still has a better implementation in shared mutex than it does in mutex because it uses more modern parts of the Windows API. So you need to watch out for that. But most of the time, just use standard mutex and be done. And unless you find problems, don't need to worry about it. Because mostly, if you've got problems, that means you've got high contention on your mutex. If you've got high contention, you ought to be redesigning your code. So standard mutex is good enough. We also have RAII types for locking. We construct them with scope lock. When they take a lock when you construct them, they release the lock when they're destructed. Scope lock is the one you should use. Unique lock sometimes because it works for specific things, but otherwise you don't need the other. Shared lock works with shared mutexes, which you shouldn't be using. So, like I say, it's a RAII type. You construct it with the mutex and it unlocks in the destructor. So Beware, it's locking multiple mutexes. You might think, okay, well, we've got a mutex and a value in 2 accounts. We're trying to transfer data. We lock both of them one at a time. That leaves you open to classic deadlock. Don't do that. 2 calls to transfer, lock them in opposite orders. Deadlock. If instead you just pass both of them to the same scope lock instance, it sorts it out. Runtime library magic just makes it work. Okay, so that's all the synchronization parts. What if we're waiting for data? Well, you really want to wait for data to be ready. You could just do a busy wait. You lock your mutex, you check the flag. If it's set, then you skip your loop. Otherwise, you unlock the mutex, lock it again, and try again. That just burns CPU cycles, so we don't want to do that. Wait electricity, it delays the notification. If the thread that's doing the generation can't get the lock because the thread that's waiting has got it, or it's competing for the same thread in the OS and for the same time slice, then it delays the notification. Condition variable provides us a way of avoiding the busy wait. It's an optimization. So this is where you use unique lock, because unique lock has this magic power that you can unlock during its lifetime and then relock it again. And so you can pass it into a condition variable that does just that. It unlocks the mutex whilst it's waiting. Then it locks it in order to check the predicate, that check the data has got value, and then it will exit that wait when the predicate returns true, and then we know that we can call process data safely. It must be notified. So we have notify one and notify all, which notify just one thread or all that are waiting, and we do it after we've set the data. And again, we do that. We have a little scope around our lock in order to ensure that everything is set up properly. Standard condition variable itself doesn't integrate with stop tokens because it's a low-level thing provided by the operating system. But condition variable any, on the other hand, does have the means of integrating. So we don't have to resort back to busy waits just because we want to use stop tokens. We can just switch our condition variable declaration from standard condition variable to standard condition variable any, and then we can pass in our lock token, stop token, along with the lock and the predicate. And this time, we need to check the return value because it might return when the predicate is false because the stop was requested. Okay, and we have C++20 also provides semaphores, which are very simple. They're counters. You acquire a slot and you release a slot. When the count is 0, then you can't acquire one, and then you can release one without acquiring it, and vice versa. They're really very flexible. You can build anything you'd like synchronization mechanism with semaphores. All of the previous ones, everything we've mentioned so far, you can do with semaphores for synchronization. If you want to know how, look up the little book of semaphores. If you get the PDF for these slides, then that's a link. But mostly you're better off using the high-level structures if you can. A binary semaphore is a semaphore with 2 states. One slot free or no slots free. It could be used as a mutex. In C++20, therefore, we've got the 2 types. We've got a counting semaphore and a binary semaphore, which is just an alias for counting semaphore of 1, though it might in practice be a specialization with more optimal code. And then also, you don't have to block. You can just try to acquire a semaphore and return immediately, or maybe for a time period or until a point in time. So, if we've got a counting semaphore with a max of 5 that's constructed with 5 free slots, so the 2 5s have slightly different meanings here, then we can then have 5 threads at most calling do stuff. So we acquire and release a bit like a mutex, but in this case there's a max concurrency level of 5 rather than just 1. Our lowest level of synchronization comes with atomics. And in C++, they're written standard atomic of T for any T at all, as long as it's trivially copyable or bitwise comparable. So it can be a struct with completely user-defined data, but must be trivially copyable. And likewise, if you compare it with memcomp, then it should give equivalent values. Floats are funny. The bitwise compare might not be equivalent to equals equals, but mostly it's all right. The only exception here is that shed pointer is allowed. Shared pointer obviously isn't trivially copyable. It's got to increment the reference count, and likewise with weak pointer, but it's deemed sufficiently useful that we can have a standard atomic of standard shared pointer of some t, and that deals with atomic reference counting for that object. It still might not be lock-free, even though it's atomic, it says. It might use an internal mutex. We have 3 guaranteed types that are, but the integers sound good, but you don't know how big they are. Are they only 8-bit? Are they 32-bit? Maybe 64-bit? Who knows? So you need to be careful of that. You're better off just checking the is always lock-free the flag for a given type. And then if you combine that with if const extra, then you can then do something else. If you wanted it to be lock-free and it isn't, or you can just do an assert. But on most platforms, anything that's smaller than the pointer is probably lock-free. So, in summary, avoid managing your own threads if you can. Use things like thread pools or the parallel algorithms. Use Jthread if you're managing your own threads. Use stop token for cancellation. Future latch and barrier are the next level down if you're having to do synchronization. Use standard mutex if you can't use the high level things, and occasionally, rarely, you might want to use standard atomic. So do that. Now it's time for questions. Before I move to answering questions, then I just want to say that Woven Planet is hiring. So my team in the UK is hiring, and we have teams in Tokyo and Palo Alto as well. So get in contact if you want to come work for us. Okay.
Anthony, thank you so much for that fascinating talk. I'm a big fan of your work, but I think as we've gone over, if we can take the questions in the lounge, if that's possible. Are you available to take questions?
Of course, yes.
Great, thank you very much. Okay, well, I guess we will see everybody over there.
Okay. See you in a minute.
Yeah.